There's only one other student on the test that's in this class?
Right. Okay.
And
3,
three
4,
in
6, 7, 8, 9. Yes, there's 9 people total. That doesn't sound right because. Oh, that's right. You're not officially in. Right. You're just here for fun. So yeah. Okay. Okay. Yeah. All right. That now makes sense. And a grade. Okay. Well, of course, one of my favorite topics to deal with is integration, and that's all that today's going to be about, and the next days after that. Okay. And this textbook is kind of strange because it has two chapters in integration. Because there's regular integration routines, the simpler-minded ones. So this is chapter 7 in the text, or 3 in the notes. And then the book has to diverge into orthogonal polynomials before coming back to the cool integration routines, like the ones I use in KSS. Okay. So, the problem we're going to look at is very simple to describe. Approximate I of f, which is shorthand, refers to the definite integral of f on some interval ab. And the idea is, of course, you learn about how to evaluate integrals in calculus too, but that's by computing antiderivatives. And a lot of times, that's not possible. Like it's beyond the techniques that you learn, or even software can do. Or you might not have f of x. You might only have its values at certain points, and you want to try to approximate the integral anyway. Now, one of the nice things about this problem is it is relatively insensitive to round-off error. So we call it a well-conditioned problem. You don't get too many of those. A lot of important problems are ill-conditioned, like certain systems of linear equations. But it makes sense because I talked about that last time. Differentiation. Differentiation is an ill-conditioned problem. If you choose like too small an h, any round-off error can throw it off badly. Whereas if there are small errors in evaluating f of x, yeah, it'll throw off the integral sum, but not a huge amount generally. So at least we don't have to worry about that so much with this problem. Okay. Now I need to describe our general approach to approximating its integral. What we're going to do is approximate it by a sum involving the values of f at certain points, x of I, which are called the nodes, and these are points chosen from the interval AB, usually, but for now we're going to assume that. This makes sense anyway. Multiplied by certain numbers Wi, which are called the weights. Okay. So the problem becomes, how should we choose the nodes and the weights in order to maximize accuracy? Now, one way to view this, and so the whole thing is called a quadrature rule. So the nodes and the weights are chosen so as to be independent of f. So it doesn't matter what integrand you're using, you're going to say, okay, I'm integrating over AB. So I choose my nodes, I choose my weights, and then whatever f I'm given, I use those nodes and weights to approximate the integral of that f. Now, you could think of this quadrature rule as a sum of areas of rectangles. So here's our interval AB, and here are my nodes, like x1, x2, I'll just pick 4 nodes. And then here's my f, and I'll evaluate f at those points, those nodes, and then define rectangles having those function values as heights and the wi's, so the width of these rectangles are given by the weights. Now, does anyone remember from Calculus 2, this kind of a sum of areas of rectangles, what do we call that? It's a Riemann sum. So you can think of a quadrature rule as a Riemann sum with n rectangles, but in Calculus 2, the heights were chosen by certain uniform methods, like using left endpoints or right endpoints or midpoints. We're not even going to talk about using left endpoints or right endpoints because they're so awful in terms of accuracy. They're not worth discussing. Midpoints are. That's actually a good way to go. But we're going to look at other ways too that are even better. Okay. And this is where the term quadrature rule comes from, that we're using quadrilaterals, areas of quadrilaterals, the simplest ones, rectangles, to approximate the integral. Okay. Now this is the first week, or this is a week when my 102 students are taking their first test. So of course they're freaking out a little bit. So yeah, I'll try. So some of you are in the zone who get to deal with that.
No, we just don't have the password for it.
What?
We don't have the password. I think he sent it to Ford and Ford sent it
It's
to
the
us.
same
She
old
just has to
password.
give it to us.
Same old password?
Yes. Yeah. I never change
I'll
it.
give it to you.
Okay.
Alright, yeah, we'll do that.
All right. Problem solved. I'll stop being a newbie.
I swear.
Yeah. Okay. All right. So we still need to determine. Okay. So now that we have this kind of setup, how do we choose nodes and weights? So as a general philosophy for how you approach problems like this and how you construct approximation methods. There's two questions worth asking. The first question is, for which cases is the given problem, in this case, evaluating an integral, for which case is the problem easy to solve? And then once you have that, the second question is, how can we, in some sense, reduce the general case to an easy case, like from question 1? And this is worth asking for any of these kinds of problems. Like, for instance, root finding, for which problem, kind of function is it easy to find a root? A linear function. How can we reduce the problem of finding a root of a general f of x to a linear function? Use a tangent line approximation. That's how we got Newton's method. So what kind of integrals are particularly easy to evaluate? From Cal 2. Polynomials. Yeah, so where f is a polynomial. Okay. So those, there's no need to approximate. We can evaluate those exactly. So now we have some other f of x that could be anything at all. we need to be able to reduce the problem of evaluating the integral of a general f to a polynomial. So what should we do in that case? Yeah.
I feel like I'm cheating though. I already know this.
That's fine. At least, well, it's showing me that you remember.
Okay.
Yeah. Okay. Yeah. So use polynomial interpolation, such as by Lagrange. All right. So in the case for general f of x, you approximate f of x by a polynomial, and then you integrate the polynomial exactly. So at least that integral of that polynomial should hopefully be a good approximation of the integral of f. And is that really true, or we're going to find out? Okay. So this gives us some guidance on how to actually choose nodes and weights. Because here we have a general quadrature rule that I haven't really specified anything about the nodes and weights, but at least now we can narrow that down a little bit. So now I can focus on a particular type of quadrature rule called an interpolatory quadrature rule. Okay. So I'm going to let Pn minus 1 of x be an interpolant, well, an interpolating polynomial of f of x at my nodes. So I still haven't told you how to choose the nodes yet. We'll get to that later. But if you've chosen the nodes at least within AB, you then construct the interpolant of your f of x at those nodes. So that means we can describe this polynomial using Lagrange polynomials. And since you have n points and nodes, your interpolant will be of degree 1 less. It'll be n minus 1. Oh, times f of xi. Usually I've written it the other way, but multiplication is commutative. Now, one notation thing, when I was covering interpolation, I would number the interpolation points from 0 to n, but it's customary with quadrature notes to number from starting from 1. But it's still the same idea, that we have n points, our interpolant degree n minus 1. Okay, so now I can say that the integral of f is approximated by the integral of Pn minus 1, and that we can compute exactly. But because the integral is linear, I can write this as a sum of my f values at the nodes times the integrals from a to b of my Lagrange polynomials. Okay. So the integrals of Lagrange polynomials on AB, those are the weights. So that's what interpolatory quadrature rules all have in common. That the weights are always the integrals of Lagrange polynomials for your nodes that are equal to 1 at one of the nodes and 0 at all the other ones. So once you've chosen the nodes, everything else is nailed down for you. And these are the only kinds of quadrature rules that we'll be dealing with. Now, all right. Now, Now suppose that f actually is a polynomial itself of degree n minus 1 or less. Then the interpolant will be the same as f. It'll be exact. Therefore, this quadrature rule will integrate f exactly in that case. So I'm going to define this term here. The degree of a quadrature rule is equal to the highest degree of polynomials that is integrated exactly using this rule. All right. So what you can say is for a given interpolatory quadrature rule, you can determine that it integrates all polynomials up to a certain degree exactly. Now, what we can say from this is, if f itself is a polynomial, if a degree is n minus 1 or less, Pn minus 1 will equal f. So, now the term degree of a quadrature rule, that can be applied to any quadrature rule, but when we're talking about interpolatory quadrature rules specifically, we can say that the degree is always greater than or equal to n minus 1. And that's because of what I said here, that if f is a polynomial of that low degree, the interpolator would equal f. So of course it's going to be exact. So what we'll find is that in certain cases, the degree might be higher. And in a couple chapters, I'll be able to tell you, here's a lower bound for degree, but in a couple chapters, I'll be able to give you an upper bound for a degree, although some of you may already know it. Yes, you gave it away. Yeah. Okay, but again, that's good you remember that. Okay, so now what I'll do is go over some of the simplest interpolatory quadrature rules. Well, in fact, I can narrow it down to a certain class of those. Okay. Right. Okay. So now I'll talk about a certain class of interpolatory quadrature rules called Newton-Cotes rules. So what sets apart Newton-Cotes rules is, it's kind of funny how Newton's so famous and nobody knows who Cotes is. And like, did they work together and then Newton kind of gave him a shaft or what? We need to look into these things. Like, what is the history here? Oh, yeah, you can Google Cotes because I've never bothered to do that. So, okay. All right. Now, what sets these apart is that the nodes are equally spaced. Okay. So now I'll go over the simplest Newton-Cotes rules. They're actually still very frequently used. Okay. So the first one is called the midpoint rule. So the number of nodes, n, is equal to 1. There's only one node. So the approximation, so our node x1 is just the midpoint, a plus b over 2. So we evaluate the integrand at that one midpoint, and then we multiply by the width of the interval, b minus a. Okay, that's all there is to it. Now, so this is the weight, W1. Now, the degree of this rule, since the degree of any interpolatory rule is at least n minus 1, so you think, okay, the degree is going to be at least 0, you'd think. But it turns out the degree is actually 1. So this will integrate constant and linear functions exactly. And the reason why is, let's suppose I have a linear function on AB. And I approximate the integral, which would be the area of this trapezoid, by plugging the midpoint in and taking the area of this rectangle. So now I'm going to have some error. I'm going to have error over here and error over here. What happens to the error? Yeah, they cancel out, because this error is going to be, like the difference between the exactly approximate, this error is going to be positive, and this error is going to be negative. By choosing, and that the picture isn't accurate, by choosing the precise midpoint, you can see from a symmetry that these areas are exactly equal in magnitude, so they cancel out. So that's why I can handle a linear function exactly. So this is an example of a quadrupole having a higher than expected degree. Also, this is an example of an open Newton-Cotes rule. And by an open rule, I mean, I want to do my precise definition here. That's totally the wrong page. Okay. Where else did I find this? This is terrible. Oh, okay. Yeah, I found it way earlier. All right. The quadrupole rule is open if the nodes do not include the endpoints A and B. Because we only have one node, and it's neither of those. It's A plus B over 2. Okay, if a rule does include A and B as nodes, then we say it's closed. Okay. So one thing we can say in general is an open Newton-Cotes rule. Okay. Okay. Oh. Nope, sorry. That's going to be a wrong statement. Never mind. Alright, this is what I get for not looking at my notes often enough. I remember things funny. Okay. Okay, I'll bring this point about degree of accuracy after I show you the other two rules. Then it'll be easier to see. Okay. Now, so the next rule of interest is trapezoidal rule. although in the textbook, they call it the Trapezium Rule, because if they're British, they have to give things snooty names. And now that's immortalized on YouTube. So in this case, we have 2 nodes. And the nodes are A and B. So that means it is a closed rule. Okay. So what we do here is so it's approximated by B minus A over 2 f of A plus f of B. So this is the area of a trapezoid. So here's your interval AB, here's your f of x, and you make a trapezoid with heights f of A and f of B. So this area of a trapezoid, what is the formula for the area of a trapezoid? It's the width of a base, B minus A, times the average of the heights, 1/2 f of A plus f of B. So that's where the trapezoidal or trapezium rule gets its name. So this number here, B minus A over 2, that is W1 and W2. They're both equal to that. So what's happening here is these are interpolatory quadrant rules too. So the midpoint rule fits f of a constant function using a value at the point A plus B over 2. The trapezoidal rule is fitting f with a linear function using a points A and B. So it's making a line from those 2 points and saying I'm approximating f by this line and integrating that exactly. And then the weights, the integrals of Lagrange polynomials, work out to be B minus A over 2 in this case. Now the degree of this rule is also 1. Because you might have thought that maybe it'd be 2, because here we have 1 node, here we only have 2. But that doesn't give us a bump in the degree, unfortunately. So it can handle linear functions exactly, but not a quadratic. Okay. And then we have Simpsons Rule. Oh, did you find anything about Coates?
Oh yeah, I totally did. The reason that, this is speculation, but he only published one thing.
Okay.
So I'm assuming that,
Which name did you look up? Roger Coates?
yeah, well, it was under the Newton-Coates rule, and then I typed Roger Coates.
That's
And
not
he only published one thing, and, so I'm guessing that's why no one knows him. And then it says later, like after he died, his cousin published a whole bunch of stuff, like a whole bunch of his stuff, so I'm guessing he wasn't like really credited with it.
It says on here, it says that, well, first,
Go
Newton
down
was
to
his
mathematics.
advisor, and it says he worked closely with Newton because he proofread the 2nd edition of the Prince.
No, go to mathematics, like down, all the way. That's what I'm
Yeah,
doing.
no, but this is his too. This is all Roger Coates. It
Yeah.
says that he invented the quadrature formulas known as Newton Coates.
Oh.
And he was the first to introduce what is known as today's Euler's formula.
Oh, interesting.
But yeah.
But yeah, why he wouldn't be known, I'm assuming because he didn't publish anything.
Oh.
I mean, or you
Oh, it came out after his death.
My thing is, were they doing this way back then by hand?
What choice did they have?
That's what I'm thinking. How did
Yeah. Oh, yeah. These guys are pretty hardcore.
they see that?
Yeah. All of us, including me, are mathematical wusses by comparison.
Right?
Didn't they just make computers because mathematicians got pretty much tired of doing this crap by hand?
Probably, yeah.
Yeah.
Yeah. Well, actually, it's probably during wartime. Like also we need to. Okay.
I mean, they were originally counting machines, right? And then they were made.
Yeah. Well, because also the word computer, before computers as we know today were invented around World War II, was used to refer to a person. It was an actual job title. So they had the Department of Agriculture needed people to solve AX equals B problems from agricultural data, and they'd be doing Gaussian elimination or whatever, be sitting at desks all day long doing that, and also they were mostly women, because women have better computational skills, whereas men have better other mathematical skills like spatial reasoning and that sort of thing. So that was the person's job title. They were a computer.
It's really funny.
Yeah. So a lot of the need for numerical linear algebra came about from agriculture. And it's
It's pretty cool.
yeah. And actually, when in the Science Museum in London, they have some of the early like Babbage's analytical engine and stuff like that. They even had something that can solve differential equations using all these levers and stuff. It was like wow.
What?
Yeah.
Levers?
Yeah. All these fun, fancy moving parts and yeah.
Oh god, that would be so fun.
Yeah.
Pull the lever
That
from
movie.
that one?
The imitation game.
Oh, dang.
Inversion group.
Yeah, where she goes, pull the lever, Kronk, and then wrong lever?
Yeah.
Yeah. Oh, you got it.
Yeah, I totally got it.
Alrighty. So, yeah, well, because Gauss, he didn't publish as much as he could have. He still published a lot for a long run. But I guess he kind of kept a lot of things to himself.
But didn't a whole bunch of people name stuff after him?
Oh yeah, well, Gauss elimination, Gauss has nothing to do with that. Somehow his name got attached. That was done by the Chinese 5,000 years ago. So I'm not sure how it happened, but
Just like everyone names everything boiler or like Pythagorean
Yeah.
something.
yeah. Well, so apparently Coates developed these rules and Newton had nothing to do with it, or
No, I think
I
it
think
says he
Yeah.
created it, but it says that they
but
were
he
like,
also
together.
says it's
Yeah.
advisors. So
He's
that'd be like
advisor.
us doing research,
Oh,
I guess.
okay, so it was like Newton the advisor or something? Or?
Yes.
Ah, okay. All right, okay. So we could have like a Lambert's Montefort.
Yeah.
Okay. All right. And attach your names to
Screw you, I put my name first.
Oh, alphabetical. So.
I would say, oh, that's the before M.
Yeah. Well, okay. Here's something from my own advisor that he developed an algorithm that was based on the Lanczos method, and so he called it Lanczos bidiagonalization. But he didn't. So Gall did not want his own name attached to it. But after he passed away, one of his colleagues insisted that it be named after him. So now it's called Golub-Kahan because they invented together Golub-Kahan bidiagonalization. So when I mentioned in a talk, I was corrected that now we're calling it this.
Oh.
And within a few years, the new name stuck. So
Oh, wow.
yeah, like I could never name it something after myself.
Oh, so someone else has to pretty much do it for you?
Well, maybe some people have presumption enough to do it, but now
I would.
no, okay. That said, I would feel more comfortable naming something after myself if also in combination, like with one of you guys. Because then I think, well, I'm attaching your name to it, and then hitching myself along for a ride. I actually seriously considered, because I just published a paper with Megan Richardson, where we have some orthogonal polynomials. I thought, well, it'd be cool to call them like Lambert's-Richardson polynomials or Lambert's polynomials or something like that. But I didn't. So
Missed your opportunity.
well,
Some people like, well, I mean, people know you already, but I feel like you would get your name out.
well,
They'd be like, oh, that's
What
your
did you
last name.
call
Oh, I've
her?
heard about this. You know what I'm saying?
yeah, because I mean, I chose to name cases methods.
Yeah.
But there's no way I was gonna put my name on that. So,
The Kissel methods. That's it.
yeah, and actually, I didn't do the acronym. Someone else put the acronym on it. I mean, I give the name Creole Associated Spectral, but then someone else started calling them KSS methods, and like, oh, okay. So, yeah. Okay. Simpsons Rule. All right. So here we use 3 nodes, and we just take the nodes from these methods. So A plus B over 2, and B. So the approximation, you fall so far behind us in class. Although it doesn't really matter because I have like 5 or 6 days left over. B minus A over 6. And we have a strange weighting here. The midpoint value is given 4 times the weight of the other values. Alright, So really the weights are, so the first one and the third one, those weights are b minus a over 6. And the second weight is 2b minus a over 3, so 4 times that. Okay. So in all three cases, what are the sum of the weights?
One.
No.
I don't know, I just guessed because I thought that's what
Well, it's not a bad guess, but no.
Wait, add them together.
Yeah.
A over 2. Oh, b minus a.
Yeah, b minus a. And the reason for that is
Could have just
similar.
looked at-
What?
So we could have just looked at the first one.
Oh, well, yeah,
Like
true.
one.
Similar to why if differentiation, the sum of all the weights had to be 0, is because what if f is a constant function? Like, what if f of x is equal to 1? Then the answer should be b minus a. And in a quadrature rule, I don't have it written down anymore, but if f is a constant, you pull that out of your sum, and what's left? The sum of the weights. So that's why it has to be b minus a. Okay. So that's something we're always going to see. And the degree of Simpsons Rule is actually 3. Even though by using 3 points, the idea is it fits f with a quadratic function. So you're passing a parabola through the graph of f at these 3 points, a, the midpoint, and b. And the thing is, with 3 nodes, you think, okay, it's definitely going to do degree 2 exactly, but we get 1 extra, just like with the midpoint rule. But the thing is, both Simpsons Rule and Trapezium Rule are closed. The midpoint rule is open. But the pattern that I can state from here, and this is what I started to state earlier and messed up, is the degree of any Newton-Cotes rule if it has n nodes is always equal to the lower bound of n minus 1 if n is even, and it's equal to n if n is odd. So we like the odd numbered rules because those give you more accuracy generally. Okay. All right.
Is there any proof for accuracy of odds? Or it's just like
Yeah, actually. So the way you can show that is using a Taylor expansion of f of x. Like if you expand it around them, because if you have equally spaced nodes and n is odd, one of the nodes is always going to be the midpoint, like we're seeing in these 2 cases. So you can expand f around the midpoint, and what you get is these error terms canceling out. And so that's how you can see why you get that degree of accuracy. Okay. And that symmetry is lacking in the case of even nodes, so that's why you don't get that cancellation. Okay.
Is that at the bottom? That's just saying that if there's n nodes, then it's an odd amount. If there's n minus 1 nodes, it's an even amount.
Kind of like the other way around. Like, yeah. So however many nodes you have, even or odd, will determine what degree of accuracy you'll get. Okay. So for instance,
Oh, if n is even, then you get n minus 1 degrees.
yes.
And if n is odd, okay.
Yeah. So 8 node Newton-Cotes rule have accuracy 7, and 9 node rule have accuracy 9.
Okay.
Yeah. So in fact, a 7 and 8 node rule will both have degree of accuracy 7. So you might as well use the 7-node rule. Although even node rules like trapezoidal are definitely not useless. Certainly the trapezoidal rule is of interest, and for reasons we'll see later. But okay, now let's look at. Well, actually, I want to do a quick example. How much time? Okay. We also want to be able to talk about estimating error.
So are those rules only for like when n equals 1, n equals 2, or n equals 3?
Yeah, so these are certain specific Newton Cotes rules. Those are the best known. And then if you want to define higher order Newton Cotes rules, you can just pick equally spaced points. And like for
There's
instance,
not like a general rule out there for anything greater than 3 or something?
there's no convenient formula. Just because these weights are the integrals of Lagrange polynomials, which get a bit more unwieldy to compute. Yeah. So something that you could compute numerically. Okay. All right. Now, so a quick example of using these rules. For a function f of x equals x cubed on 0 to 1. So this is A and this is B. So if I go ahead and use these three rules, so starting with, now first the exact value, the old-fashioned way. Okay. So that's going to be 1/4. So let's see how far off we are. So the midpoint rule, so the integral, our midpoint is going to be 1/2, and our weight is going to be just 1. So we have 1/2 cubed, we just plug that into f, so we get 1/8. So not very good. But it's one node, what do you expect? Okay. So hopefully we do better with the upper rules. So in trapezoidal, this approximation, definitely not equal. So our weights are 1/2, so b minus a over 2, and we evaluate at 0 and 0 and 1, so we get 1/2, so also pretty bad. Yeah, that's unfortunate. And then finally, Simpsons Rule. So it's b minus a over 6, and we have f of 0 plus 4f of 1/2 plus f of 1. So we get 0 from here, we get 4 times 1/8, because it's cubed, plus 1. So we get 1/6 times 3/2, and well, look at that, we got it exactly. So, but this is a cubic polynomial, and Simpsons Rule has degree 3, so we could have expected that. Let's go one step further. X to the 4th. Now, the exact value is 1/5. Let's try Simpsons Rule on that, because it's not supposed to be exact anymore. So same nodes. So now we have 0 plus 4 times 1/2 to the 4th power, so it's 1/16 plus 1. So we get 1/6 times 5/4 is 5 over 24 versus 5 over 25. So not bad. So it works pretty well. Okay. All right. So now I'm going to discuss, can we get an error formula for these rules. Just as we have an error formula for polynomial interpolation, we have an error formula for differentiation. It'd be nice to have an error formula for these integration rules. Now, the error formula for differentiation came from the error formula for interpolation, and we're using interpolation again here. So that is going to help us again in this case. At least for a trapezoidal rule. That's the easier one to handle. Okay, and then, yeah, this will end up using up the rest of our time. Okay. Okay. All right, now, all right, so first, simpler case is actually a trapezoidal rule. So the error would be the integral of your exact integrand minus your interpolant. And your interpolant is of degree 1 because you're using 2 nodes and the degree is 1 less. So that would be okay. So our error formula for interpolation would be second derivative at some unknown point, it depends on x, over n plus 1 factorial, keep in mind n is equal to 1. Oh, sorry. And the number of nodes is equal to 2. The degree of our interpolant is equal to 1. So what you have here is whatever degree your interpolant is, you have one higher order derivative over that factorial plus 1. And then we have linear factors corresponding to our nodes. Our nodes are a and b, because this is x1 and this is x2. So this is straight from the interpolation error formula. So that's all I did here. So the error in the integral is the integral of the interpolation error. Just as with differentiation, we differentiated the interpolation, the error formula. Okay. So if we can get some handle on what this integral is, we'd have an error formula.
Will you tell me how you had F prime again?
Or F double prime.
Yeah.
Okay. So this interpolation error formula is f minus Pn of x, where this is of degree n. It's always n plus first derivative at unknown point. Okay. All right. Well, no, it's okay. All right. Where whatever degree you have here, you have that plus 1 number of linear factors here. So that's why we have degree 1, but we have 2 factors, 2 nodes. Okay. Any questions about the formula before I do anything with it? Okay. Now, the nice thing is, this quantity here, x minus a times x minus b, is always less than or equal to 0 on the interval AB. Because if x is between a and b, this part, that factor is always greater or equal to 0. This factor is always less than or equal to 0. Because x is always between a and b. Right. So, when you have a factor like that does not change sign, you can use the weighted mean value theorem for integrals. And what that allows you to do is the if you have a certain part of your integral that does not change sign, the rest of it you can pull out and evaluate at an unknown point, which I'll just call squiggly. And then the rest stays inside the integral, and this right here is, we know what all that is. We can integrate. Wait, it's not 0 to 1. What am I doing? None of this is 0 to 1. It's A to B. My example was 0 to 1. Okay, sorry about that. Okay. Now,
It worked out nicely though.
Yeah,
You know,
that's true, yeah. Okay. So this integral, we can just work that out. And if you do, what you get is minus b minus a cubed all over 6. And the minus we expect because, as I said, this whole thing is less than or equal to 0 throughout the interval, so of course the integral is going to be negative. So we put everything together, and we get our error formula, and it's minus f double prime at an unknown point over 12 times b minus a cubed. So that is the error. Yeah, that is the error in the trapezoidal rule. Now, of course, if the interval AB is large, that means the error can be gigantic. But we'll deal with that another time. We also see if f is a linear function, its second derivative is 0. So we can see that the error the error would be 0 in this case if the integral would be exact. Okay, so any questions about how that was done?
So what, I mean, I understand how that minus sign came, but what does that mean? How we could interpret that minus sign there?
Oh, it just comes about because the integrand is negative.
So it's absolute value of that.
Well, yeah, because generally we care about the magnitude of the error. We don't really care whether it's positive or negative.
Yeah.
But yeah, it can give you an idea as to whether your approximate integral is an upper or lower bound on the exact answer. Like if you know something about the sign of the second derivative. Like if you know the second derivative is positive, then you can say that your approximation is an upper bound, for example. So that's the only time a sign of an error, positive or negative, might be useful information. Okay, now, in the last 15 minutes, I'm going to do a rather freaky proof. Because unfortunately, what we did here, to use a weighted mean value theorem for integrals, we cannot do the same thing with the midpoint rule or Simpsons rule. Now, there's a rather strange proof in the textbook about Simpsons rule. And what I did in one of my prouder moments, teaching-wise, is I figured out how to adapt their proof to the midpoint rule. And that's what I'll show you. Because if I were to do the same thing, if I were to try the same approach, with the midpoint rule, the error using a interpolation error formula would be integral from a to b, just plain old f prime at an unknown point over 1 factorial, and then I would have x minus a plus b over 2. And here's the problem with that. This changes sign. It goes from positive to negative in the middle when x varies between a and b. So we cannot use a weighted mean value theorem for integrals, unfortunately. Now, if I had actually covered divided differences in this class, I'd have a not so difficult fix for this, but I haven't. So that's why I'm doing this really strange proof now. Okay. All right, so I'm going to make an assumption. We assume that f is twice continuously differentiable. I don't feel like writing it out on AB. So because our error formula is going to involve a second derivative eventually, which we expect because, like Trapezium Rule, this is exact up to degree 1. And then I'm going to make a change of variable for convenience. So I'm going to make a change of variable from x being in the interval AB to t in the interval -1 to 1, just for concreteness sake. Okay. And then I'm going to define big F of t to be little f at x of t. So I'm mapping my integrand also to the interval -1 to 1. So now I can say that the error in the midpoint rule, which the error is going to be my exact integral minus what I would get from a midpoint rule, which is b minus a f of a plus b over 2, that's the same as if I basically make a u substitution in here for my true integral. Integrating f, little f from a to b is the same as integrating big F from -1 to 1, as long as I have this factor of b minus a over 2 that comes from my change of variable. So that's the straight Cal 2 u substitution stuff. And then the midpoint rule applied to this integral, well, my length of my interval is 2, so that's my weight. And then what is my midpoint? It's 0. So this is my midpoint rule approximation in this particular case, when I'm integrating working with -1 to 1. Okay, so now I have this expression for the error.
Is that a tau?
Yes, it's a tau.
Okay. That's tau. Where did it come? T? Is that the same thing?
Yeah, it's just that, yeah, using my tau as my integration variable
Right, okay.
for functions of t. Okay, and that's because I'm going to need t elsewhere.
Right.
Okay, so now, here's where things start to get really weird. I'm going to define this function, g of t, okay, to be the integral from minus t to t of f of tau minus 2t f of 0. So it's kind of like I'm now taking this expression inside the square brackets and I'm making it more general. And as a result of that, I can say that the error is equal to b minus a over 2, this b minus a over 2, times big G of 1. Because now if I were to take t equal 1 in here, I get exactly this. So that gives me yet another expression for the error. I figure if I keep rewriting error, eventually I'll be able to figure out what it is. Okay. But this is basically going to be proof by calculus tricks. And actually there's similar calculus tricks that I've used for other things. All right. Okay. Now, since I haven't defined enough weird stuff, let's define more. And hopefully I get through this in 9 minutes. Well, okay, I have 1 page. It's ambitious, but we'll see. All right, let's define another function. Big H of t is g of t. I'll subtract off t cubed g of 1. Okay. Now, what is h of 0?
Zero.
It is 0. Now, to see how you get there if you're not sure, it's because this term is obviously gone. We have g of 0, but g of 0 is the integral from 0 to 0. Which would be 0. Okay. What's h of 1?
G1.
Zero?
G of 1.
Because you get G of 1 equal, G of 1 minus
Oh,
G of 1 is
zero.
0.
Okay.
Yes, it is 0. Okay, when a function is equal to 0 at 2 points, that invites us to use what?
What's it in?
If a function is equal to 0 at 2 points, that invites us to use what from Calculus 1? What theorem? We used it before.
Rolls?
Yes, Rolle's theorem. So,
I remember seeing.
Rolle's theorem says that h prime at some unknown point, which I'll call squiggly 1, is equal to 0. All right, but now, and also it's between 0 and 1 where that happens, because h is definitely not constant. Okay, now, though, let's take a look at h prime of t. H prime of t would be g prime of t minus 3t squared g of 1. But look how big g is defined. It's defined as an integral. So by the fundamental theorem of calculus, when you differentiate an integral with respect to its limits, because I'm differentiating with respect to these guys, that would be big F of t, and then minus big F of minus t times the derivative of minus t, which is minus 1. So that would be big F of t plus big F of minus t. Okay. So, all right. Something is strange here. 3t squared, 3 of 1. Okay. I can't forget this. Alright, that's going to be minus 2 big F of 0, because you're differentiating with respect to t again. Okay. Now, so now I have, and then, okay. So what would big H prime of 0 be?
Zero.
It-
Because f of 0 plus f of 0 is 2 of 0 minus 2 of 0.
Yes. And then this would go away because we're plugging t equals 0. All right. Questions about that? I said some uncertainty.
No, I said I was uncertain at first, and then Vivian said,
Oh, okay.
Yeah.
Yeah, because we have f of 0 plus f of 0 minus 2f of 0. And that
yeah.
makes everything go away. All right. So now we have h prime is 0 at a point, and at 0, and h prime is also 0 at this point at c1, which is greater than 0. We use Rolle's theorem again. So we can use, so from this and also this, put those two together with Rolle's theorem, that h double prime at some point, which I'll call squiggly 2, is 0. And that is greater than 0, less than squiggly 1, which is also less than 1. Okay. But now, what is h double prime? H double prime of t is g double prime of t minus 6t g of 1. And I can differentiate that. Now, that would be f prime of t minus f prime of minus t by chain rule. And then this would be 0, differentiated. And then I still have this. Okay. All right. So, what the? Okay. Oh, gotcha. All right. But now I can do something with this. This is equal to, by mean value theorem, so I just get all the calculus 1 theorems. They're really great tools for classes like 772. This is equal to t minus minus t times the derivative of this at some unknown point, which I'll call squiggly 3. I swear to God, that's my last squiggly. So I can simplify this. This is equal to 2t f double prime of squiggly 3. But the thing is, h double prime is equal to 0 at a certain point. So 0, which is h double prime of squiggly 2, is equal to 2 squiggly 2 f double prime of squiggly 3 minus 6 squiggly 2 g of 1. I can't do my squigglies anymore because I'm too tired. Okay. All right. Now, what is g of 1? Because now what I can do is I can use this equation to solve for g of 1. So g of 1 is equal to, so I can like move this to the other side. So I can say that g of 1 is equal to 1/3 f double prime of squiggly 3, because the squiggly 2's cancel out. Okay. Now, what is this? This is, okay, 1/3, and then big F prime, I want to write back in terms of little f. So that would be little f double prime at x of squiggly 3, because squiggly is a t value. But by chain rule, because big F is defined on -1 to 1, little f is defined on AB. So I have to include a factor of b minus a over 2, and then I have to square the whole thing because I differentiated twice. Chain rule. Okay. Now, the error is b minus a over 2 times g of 1. So finally, from this, I can conclude, and I guess if you're from Math 500, this is an example of when I get myself into a corner of bad board use, because I don't have any good place to go. I'm going off the edge. All right.
What about that space on the left?
Yeah, fine. Okay. Ooh, shoot, I'm 1 minute past time. But, okay. Okay, I want to leave this here. I can erase everything else. All right.
Yeah, I was talking about that little,
Yeah.
lowered diagonal.
Yeah. Okay. So the error is equal to all of that times b minus a. So you work all that out and you get b minus a cubed over, and you get factor of 2 times 3 is 6 times 4 is 24. F double prime at some unknown point that I'll call eta, where eta is within AB. So it's similar to the error in a trapezoidal rule, except for a factor, well, a different sign, no minus, and a factor of 2. So generally, midpoint rule is twice as accurate. And also it uses one less node, so that's a good deal. And that's midpoint rule. And Simpsons rule, you'd have to use a similar approach, only it's way uglier. So it is done in the textbook. So the error in that case is minus fourth derivative at an unknown point over 90 times b minus a over 2 to the fifth power. Okay. So those are the errors in these basic Newton-Cotes rules. But as you can see, if the interval AB is large, the error can be large. And so that's will lead to composite rules for next time. Also, there's a reason why I've only talked about low degree Newton-Cotes rules, only up to degree 2. To think, oh, you can define them for any degree. And you think, oh, that'll just make it better, right? No. So since I'm way past time, we can talk about that on Monday. So, but at least I'm still just one day behind.
That's okay, we forget.